Today we're going to talk about why our channel is called Strength, Stability, Stiffness, and I hope you stick around to the end for the bonus technical fact. Like any profession, there are a lot of different ways that structural engineers can decide to do their work, or that a standard can be set by an authority having jurisdiction, such as the city or the state, a province, a government in general, even an engineering body. I work in Ontario, and as a professional engineer of Ontario, I'm actually a member of a self-regulating profession. That means that, generally speaking, it is engineers who set the standards to which other engineers must work. Now, as a structural engineer, I have a fairly simple way of trying to explain the core things that matter most to young engineers in our industry, and also to how I discuss it with clients. And that's actually the origin of the name of this channel. I always say that structural engineers must concern themselves with three things: the strength, stability, and stiffness of anything they're doing. Strength means that it has the capacity to handle the loads that are imposed by what's been placed on it when it's in service. The expected loads from wind and seismic and earthquakes, and from seismic and earthquake are the same thing, but effectively anything that it's going to undergo in service and doing its job. Then stability is something that often gets missed. Even when you look at structural engineering theories online, the lists of structural engineering theories, including Wikipedia, which I actually like quite a bit, doesn't even mention stability. It's not even in there. And that's frustrating for me because it's one of the core things that's actually most important. Load paths and the way things work together have to provide something that is stable. It's not good enough that something be strong enough and rigid enough to hold the loads. It also has to be able to not topple over. That might seem obvious, but as something that you actively think about as an engineer when you're doing your work, it's a useful measure of your design's veracity, effectiveness. Anyway, it's a very important part of it all, so it's a good thing to make new engineers, and generally yourself, of course, consider in the course of your work. Stiffness is actually about the material properties fundamentally. It's an issue of geometry and of the modulus of elasticity. This is kind of how elastic a material will be. And it governs things like excessive deflection. So when you put a beam in place, the dead load causes it to curve. They kind of smile at you, which is a creepy thing, and that's the intent. I try to make people think buildings shouldn't be smiling at you. They're curving too much. They've got a deflection issue. Also, excessive deflection can cause problems where it cracks linings and different things in the building, which can breach what we call serviceability limit states. And of course, vibration and dynamics come into a lot of deflection. When you're looking at a heel fall vibration in particular, large masses on a floor, if the floor isn't very stiff, can cause the floor to vibrate in a way that's unacceptable to most people. That might even make them feel stomach sick or just uneasy when they're in the building. There's a really good design guide by Allen and Murray called Design Guide 11, which actually is from the American Institute of Steel Construction, as well as some other standards by the Advanced Technology Council and a variety of standards out of the UK and Europe if you're looking for work on vibration. But fundamentally, remember that mass doesn't help you, stiffness does. So in the title of this video, we talked about the 8 things you really need to worry about as a structural engineer. Well, everything you're doing, you have to be thinking about strength, stability, and stiffness. Those 3 are never something you can ever get away from. But how do you do that in your work? Well, our method for thinking about that is something called DOUCE. Everything we do when we're providing those things that are strong enough, that are stable, and that are stiff enough, we must also make sure that they are DOUCE. D-O-U-C-E. Durable, overt, useful or utilitarian, constructible, and economical. So here's how it works. Triple S, the strength, stability, stiffness, and DOUCE. Durable, overt, useful, constructible, and economical. Durable is quite straightforward. You have to meet all of the durability guidelines as well as provide something that's going to give good service over a period of time in the environment to which it'll be subject. Houses in Florida are very different from houses in Northern Ontario. These are 2 very different worlds in terms of environment. Overt, this is the idea that when you're drawing something, you have to have a reason for drawing it. We put every detail only in one place. We don't talk about 2 technical details in different locations. That just leads to confusion when there's revisions. You change one, you don't change the other. We see that as a classic mistake in our forensics work. We see other engineers make that mistake all the time. And we're only human. I'm sure it happens here too. I'm just saying that in our work, we see that as a common mistake. Utilitarian or useful, What you do, what you're designing, what you're drawing has to have a purpose. We don't put extra load paths that aren't required. We don't use additional material beyond what's necessary. We don't include things because they're better for us. We include things because they're necessary for the client. Constructible, this is the idea that there are certain ways you can put a building together on paper that just won't work in the real world. It has to be something that you can actually build. And that's an interesting one because ultimately, in many different types of legal systems, you can wind up in trouble if what you've issued as an engineer isn't something that can actually be built. And economical is very straightforward. Anybody can build a pyramid. We should be building an efficient structure that contributes to the economy and does not cost the economy disproportionately. I hope that makes sense, and I hope you find it useful. Triple S DOUCE. Today's bonus technical fact relates to stability. We're going to talk about bifurcation. A lot of engineers don't realize or remember or understand necessarily that the bracing force, the amount you need to hold something straight against buckling out, is 2 to 2.5%. Now, there are very complicated ways of figuring this out, but that rule of thumb has held true for a very long time. But what's happening when you've got that mechanism, that buckling? What are you preventing? Well, it's about equilibrium. The system should be in stable equilibrium. Stable equilibrium, you can picture a marble at the bottom of a bowl. As the bowl becomes more and more flat, you transition from stable equilibrium to unstable equilibrium. If you had that same marble at the top of a hill, any little force could cause it to roll away. The point at which you transition from stable equilibrium to unstable equilibrium, that's the point of bifurcation, and that's what you need to avoid in your work for stability.